Hi, everyone. I'm Max. I'm a researcher at Google DeepMind, as Nemanja said. And today I wanted to share some context about context in the context of large language models. So as you can hopefully tell, there's going to be a lot of context involved. And I want to take you back quickly to 2016-17 when I was a master's student at UCL in London. And I was doing an internship at a company called Bloomsbury AI. And this company kind of spun out of UCL. And initially, we were working on question answering through something known as retrieval. So imagine you have users, which for a very early stage startup is a very good thing. And your users have interesting and important questions, such as what time does the swimming pool open? And luckily, you have access to like a highly curated corpus of question-answer pairs, which typically your kind of enterprise customers have compiled and put together. Maybe they're available on their websites. And you want to try and answer the user's question. And one approach you could take is to match that user query, so what time does the swimming pool open, to every single question in your corpus. You can score kind of all of those matches based on some kind of similarity. Back then, cosine similarity was very popular. And then you could find the one that has the highest kind of query similarity score to the user's question, retrieve that question answer pair, and present the answer that you've retrieved as the answer to the user. So in this question, the user asked, what time does the swimming pool open? The closest question we had in our corpus was, where is the swimming pool? And our answer is, the main swimming pool is located on the ground floor of the west wing of the complex. To access it. And so you're giving the user this very detailed, very interesting answer. And that's great, right? We've just solved question answering. Except that's not really what the user is interested in. The user wants to know what time the swimming pool opens. And in fact, the actual answer is contained somewhere in this kind of pre-prepared response. And in this case, the swimming pool opens at 7 a.m. And this is what we kind of proposed at the end of my first week at Bloomsbury AI. And so I spent my weekend hacking a demo together. We used a kind of very basic CF-IDF retrieval system and a machine reading model called bidirectional attention flow. And this had a particularly interesting architecture, which I'll dig into quite at a high level, but just to set some context for some of what's coming next. So there were two components to the model input, the context and the query, where the context was the passage. In this case, it was the answer we had previously retrieved as the response to the user question. And you'll notice it had things like a word embedding layer, where we had these pre-trained glove embeddings, which gave the model semantic information about what words mean. And pre-training back then had a kind of different connotation to what it means today in the context of large language models. And it had a very interesting backoff to character embeddings through a CNN encoding layer, which you can kind of think of as serving the same purpose as subword tokenization does today. You'll also notice that it had a contextual embedding layer, and it also had an attention flow layer. So this was I'd say 2017, early to mid 2017, and already kind of the architectures at the time were highly dependent on attention. This wasn't quite self-attention, but in some sense it was extremely similar, because you had two attention layers, one where the query could attend to the context, and one where the context could attend to the query. So pretty much all tokens across context and query could attend to each other. And this demo was very simple. It looks something like this, where you would ask a question, such as who was the first computer programmer. It would you could either like provide a document in the as a URL or as plain text, or if you provided nothing, it would like run a web search the internet, find the most relevant document to the user query, and then extract that answer from those documents. It could also do things like tell you how confident it was in the answer, which was a very nice feature, I thought, but never really caught on. And so we combined retrieval with early deep learning methods to effectively create what, as far as I'm aware, was the first commercially viable retrieval augmented deep learning system. And we call it CAPE. It was targeted towards the legal and financial domains. We also had a conversational agent. We had a Slack bot. It was all kind of very sophisticated. And that was around kind of mid-2018 when it was at this stage. So stepping back to the model architecture, there was one kind of quite particularly interesting limitation. So again, you have these two components of the input, context and query. And the query is the sequence of tokens provided the user, and context is kind of the sequence of tokens that provides the model the information it needs in order to be able to answer the query. And one thing you'll notice about the query and context embedding layers is that they were RNNs, in this case LSTMs, which is a kind of particular flavor of recurrent neural networks. And recurrent neural networks have this property where the hidden state at the kind of current time step is paused into the next time step. And you feed in words one at a time, and the network effectively loops back on itself, allowing information to persist over time. The weights of the network are shared across time steps, so U, V, and W, and model size doesn't increase with input size. And so in theory, RNNs can handle infinite contexts, which sounds amazing. The problem is that in practice, they suffered from something known as memory decay, and they also suffered from recency bias. So in practice, you could only really have maybe 200 or 300 tokens or words in the context. And this practical constraint put a lot of stress on the retrieval component of the pipeline, because basically if your retriever could say retrieve one document at a time, and that document was 200 or 300 words, then you could only really put the highest scored document as the context for your machine reading model. If the model could handle more longer context, you could maybe retrieve the top 5 documents and pass those as input to the model. And so even though we're using many of the tricks available at the time, things like chunking, where you're segregating parts of documents by kind of paragraph boundaries or sentence boundaries, combining sparse and dense retrieval to try and squeeze the most out of the retrieval aspect, query expansion, where you can rephrase or add words to the query to make it more likely to match an existing document. We had a very limited context window to work with. And then in very early 2018, a team at Alibaba released an ensemble model called SLQA+, and another team at Microsoft Research Asia released RNet. And these both kind of built around the concept of self-attention nearly a year before BERT, and they both outperformed humans on the exact match score on this dataset called SQUAD, which was very popular at the time, the Stanford question answering dataset. And the media kind of ran with it. There were these fantastic taglines like robots can now read better than humans, and is there anything that humans can do better than robots, and the robots are coming and they can read. This was January of 2018, so over 7 years ago now, which is almost unbelievable. And so for the second time in 2 years, question answering was solved again. But not quite, because 2018 was a very interesting year, and in very quick succession, so ELMO was February of 2018 by the Allen Institute for AI. OpenAI's GPT was released in June of 2018, and BERT was released in October of 2018. So in quite quick succession, three kind of very important models, all pre-trained. Elmo was also RNN-based. OpenAI's GPT and BERT were both transformer-based. And they weren't sequential RNNs. They had a fixed context window. And in the case of both GPT and BERT, they had an input size of 512 tokens, which was great in that in practice, you had more usable context than you had previously, but it was still extremely limited. And diving into pre-training quickly, because both GPT and BERT were pre-trained models. So basically, they were trained on many billions of tokens at the time, and trained in GPT's case to predict the next word, and in BERT's case to predict masked-out tokens. LLMs today are trained on tens of trillions of tokens sourced from kind of all forms of data, and they're trained using something called next word prediction. So imagine you have this sequence of tokens, planes crossed overhead, leaving long blank. And if you paid attention to Serafina's talk yesterday, you probably know what the missing word is. Any ideas? I heard it somewhere there, chemtrails. Excellent. And by doing this over and over again, for many trillions and trillions of tokens, you can teach kind of these big, very large models lots of interesting things just by getting them to predict what the next word should be. So this slide is borrowed from Laura Rees, who I've collaborated with very closely. And I want to give you some ideas of the things that models can learn from predicting the next word. One is semantics. So the sun is shining, the skies are blue, it's a blank. In this case, you can probably beautiful day. And to be able to know that beautiful comes next, you probably need to understand something about what the sun is, what shining means, what the skies are, what the skies being blue means, right? If the sun wasn't shining and the skies were gray, you'd answer that quite differently, or the next word would be quite a different one. Another is syntax. So this famous example from Noam Chomsky, colorless, green ideas sleep. Any guesses? Furiously, I heard it there again. You might have heard this one. Semantically, the sentence doesn't really make much sense, but syntactically, you know that an adverb kind of needs to go in that position. And so by predicting what that next word is, you're learning something about the structure of language. Other things like pragmatics. Joe is meeting a woman tonight. She is his maybe date in this case, right? If she was his wife, it might be phrased differently. Things like facts. Birds can fly, birds can eat, birds can't scuba dive. World knowledge. If you drop a glass, it will likely break, but if you drop, say, a ball, it would likely bounce. And reasoning, and this one this one's a race. Let's see how much you're paying attention. So the speed of a car is 120 kilometers an hour in the first hour and 70 kilometers an hour in the second hour. The average speed of the car is... No one wants to get it wrong. "95, excellent. Which is a very specific response, right? And it's very straightforward to figure out whether that response is correct or not. 95 is correct and 96 is incorrect. And by training models to predict what the next token is in these kind of correct situations, then we're teaching the models something about basic mathematics, mathematical reasoning, all of that. I quickly mentioned this work, which Laura led. And it turns out that we can even teach models some aspects of reasoning from procedural knowledge in pre-training data. So procedural knowledge is text information that basically explains how something is done, right? It conveys, say, the method of how to approach a particular problem. And in this work, we used influence functions to try and understand which documents in pre-training impacted the way the models behaved most at test time. And we had these two sets of queries. We had factual queries, which looked something like, what is the tallest mountain in the world? And we had reasoning queries. In this case, we were using things like relatively simple mathematical reasoning problems, like what is the slope of the line? And for the factual queries, you'll see that typically for each query, there was maybe one or two documents which carried most influence. And typically, the queries that were most influential had the answer to the question contained somewhere in the document. With the reasoning queries, it was much more complex and much more nuanced. The kind of distribution of relevant and influential pre-training documents was much more spread out. And the kind of information those documents contained was much more interesting and also tended to contain procedural information about how to solve the problem rather than the actual answer. So say, what is the slope of the line through 9328 and 7447? And what you tended to get was things like, code calculating the slope of a line, mathematical equations calculating the slope of the line, text descriptions explaining how to calculate the slope of a line. And we also had a control set to make sure that, the model wasn't actually doing this because it couldn't find documents that contained the answer, because maybe the answers were more spread out. And in fact, what we found was that wasn't what was happening. The procedural knowledge was somehow teaching the model how to reason procedurally. Okay, so there's clearly a lot that LLMs can learn by simply predicting the next word from many trillions of tokens. But going back to kind of the facts and world knowledge, what you effectively have at this point is a very powerful autocomplete model, which knows how to predict the next word, but doesn't really know how to do much else. And in 2020, Patrick Lewis et al. Introduced this idea of retrieval augmented generation, primarily focused on improving kind of factuality and correctness for knowledge-intensive tasks. And back then, even early models, which kind of were trained through this pre-training and fine-tuning paradigm, had various challenges, right? One was it's very expensive to update knowledge that's stored in the model's parameters. So all this knowledge we mentioned that you can acquire about the world, that knowledge is literally stored in the model's weights. And say you're training your model on a scrape of the internet from 2020, and you ask it who the president of the United States is, the model will contain that knowledge at that point in time. And if the president changes, there's a very expensive way you can update the model, which is typically to retrain it from scratch and making sure you've excluded all the outdated knowledge and only kept the updated knowledge. And that's very expensive because these models are very big and they're trained on many trillions of tokens. And the idea in RAG was, well, what if we just pre-train the model as kind of a separate, isolated step, and then used an updated source of non-parametric knowledge. So in this case, that's these documents. And those documents can be kept up to date. Those documents can also be updated on the fly. If your documents are wrong, which, as you probably expect, most of, or a lot of the kind of content on the internet is not strictly always correct or always perfect, updating the knowledge the model has access to in text space without having to retrain is a lot cheaper and a lot more efficient. And so the idea was, well, can we combine retrieval and these really powerful generative models that were starting to emerge at this time, and get the best of both worlds, right? Both the parametric knowledge that the model has about understanding of language, understanding of basic semantic concepts, ability to reason, at this stage still kind of quite at an early surface level, and combine that with a document source that could be kept updated, that could change over time, that the model knew how to access and use. And that's really what RAG introduced. So there was kind of two pre-trained models. There was a dense passage retrieval model as the retriever, and there was a BART model, both which were like kind of state-of-the-art for retrieval and state-of-the-art for generation at the time. And you had this kind of learned latent retrieval where you didn't need any labels for the documents. You just use the documents to answer the question, and then if the question was correct, you pass that signal back all the way through to the retriever. And I think that's a particularly interesting point about this approach. So it's very flexible, and you could do things like, freeze just the retriever so you don't update the retriever. You could do things like just freeze the generator. And what they found in one of the ablations in this paper was that full end-to-end training of both the retriever and generator gave you the best results, particularly on these open domain question answering style questions. And so this is taken from table 6 in the paper. If you look at the RAG token frozen and the RAG sequence frozen, results that jump when those are unfrozen, which is when you're also learning the retriever, is quite substantial. This is interesting and also quite challenging, because it means that in order to be able to do this, the information from the generator needs to be passed back to the retriever, and you need to be updating both at the same time. With today's systems, that has become a lot more challenging to do, mostly because the timeframes for training these systems have kind of expanded massively. And also, you create this interdependency between the retriever and the generator. And also, the generative models tend to be very, very large. And so what typically happens today with LLMs is you treat the retrieval component and the generative component as entirely independent, and you pass in the retrieved documents as part of the context to the language model. And then you basically tell the language model, hey, I've retrieved these 3 documents, these 5 documents, these 10 documents, whatever it is, that are relevant to the user query. Answer the user query to the best of your abilities. So this is often a much simpler kind of integration of the full pipeline. There are variants of this. You can do things like put the documents at the end. You can figure out how to rank your documents based on the retrieved scores. You can provide additional information about which documents are kind of primary sources of information and which are secondary. So there's more you can add on top of this, but the basic framework is the context to the model includes the retrieved documents and the query. This also makes it much easier to train generative models which can handle multiple types of retrieval, right? So you could have retrieval based on word overlap, you could have retrieval from a web search, you could have retrieval from a highly curated document corpus which you trust very much. And you can train the model, the generative model, to work with all of those systems without having to update all of those systems independently, and also by combining information about those systems. So you could, as part of the context, inform the model something like, this document is from this highly reputable source. These documents are from a web search. I'm not sure if I would trust them as much, but they might be useful information for you. And so there's a lot of flexibility that you get through this approach. So earlier in this talk, we defined kind of context as the sequences of tokens that come before and after a query. And in the second half, we'll explore some interesting things you can use those token sequences for, as well as some challenges. Um, so one very interesting thing you can do today, which you couldn't really do with a maximum context window of 512 tokens, is parse very long documents as part of the input. Now, there's some debate as whether this counts as a user query or whether this counts as context. Some people will say, summarize this document is a task description, and the kind of document that you want to summarize is a retrieved document or is context rather than part of the prompt. But you can do things like summarize really, really long documents. You can do things like extract information from like long, complex financial reports. You still tend to have various challenges. For example, a lot of the way we evaluate LLMs today is based on, let's call them more traditional NLP tasks, which because of the limitations of the models at the time, weren't primarily oriented towards long context tasks. You can also build conversational agents. And if you think about it, a conversation history is effectively all part of the context, given the current kind of user query and the response that the model is expected to generate. So this is from work we did in 2018, where it's kind of goal-oriented information-seeking conversation, so it's quite targeted. And the user query is, can I use the loan for this expense? There's like this document about what you can and can't do. There's kind of a scenario describing the user situation. And then there's a conversation between the model and the user, making sure that the model has all the information it needs to provide the final answer. And this kind of task, especially as the context, as the conversational history gets longer, if you're constrained by context, you quickly kind of run out of tokens effectively to provide the full relevant context of the conversation. Then we have in-context learning, which was introduced in the GPT-3 paper. And the general idea here is you're providing examples of what you want the model to do. And the model will then follow the kind of style or the task that you've defined through the examples. So in this case, we have like a string reversal example. We have 4 in-context examples. So this is like a 4-shot task. And then the model, by kind of looking at that, can figure out what the task should be. And this is very interesting, both because it requires much longer context than what was available previously, and also because it only tended to work well with larger models when you scaled up to like the 100 billion plus parameters. Even then, there's so you hear of kind of 0-shot task performance, which basically means you only provide the task description and the current example that you care about. 1-shot is if you provide 1 example. This is a 4-shot example. The number of examples you provide tends to give improved performance, but then again, you start to hit the problem of running out of context. And this is a relatively straightforward example, but imagine you had, summarize a book and you try to give 100 examples of book summaries. At some point, you would probably start to run out of context. And another really kind of fantastic phenomenon of in-context learning, which is similar motivationally to what we spoke about with RAG, is that you don't need to update the weights, right? You can, what it basically allows is generality, and you can provide examples of any task, and the model would probably perform that task to some acceptable degree of performance. And so typically, language models today extract signal from training data in 3 stages: pre-training, instruction following, also called supervised fine-tuning, and through verifiable reward. And within context learning, there are no weight updates. You don't need to do any kind of expensive training. You can just provide new examples for a new task that you just defined, and the model may or may not do that task well. There are still challenges with that approach. This is one of them. So this is work we did in 2022, won an outstanding paper award at ACL. And here what we were exploring was, what about in-context learning allows models to perform well at specific tasks? And one of the things we were wondering about at the time was, does the ordering of the examples matter in any way? And is it kind of correlated with, say, if you gave the model the most interesting examples or the most correct examples first, how does that impact performance? All of these kinds of research questions. And in one of the experiments, what we did is we got these 4 in-context examples. The kind of train and test definition is how people approach the problem at the time. Basically, you would use examples from your training set as your in-context example, and your test example was the one that you cared about the answer to. And we perturbed the order. We passed them to a pre-trained language model, and we looked at what the model generated. And if the model was robust and reliable, what you would expect is that it would get the same answer right all the time, right? If we go back to this example here and I switch the order of those 4 examples, it shouldn't have a meaningful effect on model performance. In fact, what we found was that model performance varied pretty massively. It's worth noting that both of these are binary classification tasks, so there's only 2 labels. So it's relatively straightforward, and performance fluctuates kind of all over the place, pretty much from like random baseline to like near 90% performance on some tasks. And one interesting thing we noted is that like the variation was smaller for the larger models. So like GPT-3 with 175 billion parameters actually performed pretty well, quite consistently. But clearly there was, something amiss, let's say, in terms of how the model was processing this information to provide the answer. And in contrast, just as kind of a mental reference point, different initializations of your SFT data set, which often meant a different ordering of the data that the model was seeing during fine-tuning, would give you around the 1% standard deviation. And so, going from like below 50 to near 90 for some of the models is very different to like a 1%. Another thing you can do in context is chain of thought prompting. And this is from the original chain of thought paper. On the left, you have standard prompting at the time. So you have a question answering task, you have a one-shot example, you have a question, and you have the exact answer. And what they did in this paper is they provided the model with a kind of step-by-step breakdown of how to approach answering the problem. And so what they're effectively doing is in-context learning and telling the model approach problems by breaking it down step by step. And what you tended to see was pretty massive and sometimes unbelievable performance improvements, especially on kind of specific, more complex, more kind of mathematical, more reasoning-oriented tasks, and especially with the larger models. Nowadays, this behavior is often elicited zero shot, and you tell the model something like, think step by step, and there's various hypotheses for why this might be. One of which is the model has seen so many of these chain of thought style examples now because it was so popular that you don't really need examples for the model to know what thinking step by step means. You can just tell it what it means. And so one note here, since we're talking about reasoning, is that I like to think of reasoning as in-context adaptive computation. And what that effectively means is that there's all these behaviors that models don't learn from pre-training data. So we mentioned all the things that you can learn. There's lots of things that you don't learn, such as planning, acting, improving. And this is because the data we're training on doesn't capture the process of creating the document. It only captures the final state, right? Say you have a Wikipedia document, and it's highly curated, it's checked for factuality, all of these things. models don't really go through the process of creating a document like this from scratch. They see this document and they're trained to predict the next word one at a time. And planning, like writing a sketch outline for how you're going to go about writing your document, refining it, correcting mistakes you might have made, self-verification, all of these things aren't captured in pre-training. And that's part of why reasoning recently has been proven to be so effective, in that we're effectively teaching the models new skills, new behaviors to improve their final output. And one thing we're noting is when it comes to generating the final response, all the kind of thinking tokens, all the reasoning traces that the model generates, all the planning, all the acting, all the improving, all the self-correction, those are effectively part of the context, right? They're tokens that come after the query, which help the model provide a more accurate, a better, a more correct final response. So one other area I think is really, really exciting is in context personalization. And personalization is interesting because people have been speaking about it since, LLMs became a thing. And I don't know if I'm aware of a system that does this really well yet. And personalization can also be very difficult and very expensive to achieve if you had to do something like, fine-tune a different model for every individual on the planet. Even if you had to use efficient methods like LoRa, obviously if you had to pre-train a model for every individual on the planet, that would probably be entirely infeasible. But one thing you can do is provide information about the way the model should adapt its response to a particular user in the context. And if you can train a model to do this well generally enough, then you can get in-context personalization. So in this particular setting, say you have information about the user, say you have information in some kind of text memory, some scratchpad that maybe you've built up over time through interactions with the user. And the user's query is something like, give me a research idea, but the research idea I might be asking for is probably quite different to the research idea that you might be asking for based on your preferences, based on your individual interests. And speaking about challenges with kind of personal preferences and human feedback, this is work that Tom Hosking led in 2024 called Human Feedback is Not Gold Standard. And what we did here is we tried to figure out, in this setting of collecting human preferences, where you give a user a prompt and two model responses, and you basically ask them which they prefer, A or B. What were the contributors, what were the parameters that were influencing how humans judged their preferences? And you'll see that things like refusal have a massive regression weight, and things like factuality, which users tend to say is really important, actually isn't influencing human preference, which is this data that we're training on in RLHF, very highly, at least compared to things like formatting and style. And then on this plot here on the right, we ran this other experiment where we prompted the model to either answer more assertively or less assertively than kind of the standard baseline, where it was just given the user query. And what we saw was that the human judged error rates dropped really massively as assertiveness went up. So as the model sounded more confident. And this was very interesting, right? Because the drop-off is really quite apparent, like a close to 40% error rate when the model is not sounding confident, to near zero when it is pretty huge. And so Tom dug even deeper into this and ran a kind of manual verification check, looking at what, from an expert annotator, in this case Tom's perspective, the error rates actually were. And it turned out that the error rates when the model was more assertive were actually even higher than when the model was less confident. But by sounding confident, that kind of additional confounder made humans be more likely to judge the model as being better, even if it wasn't. And that's one of the things that you might be able to correct for in context. Another aspect of the nuances of kind of human feedback and individual preferences are from this quite large study. So this is a study from PRISM, which Hannah Kirk led, just won a Best Paper Award at NeurIPS. And this was a very large study, ran over 2 years. There were 1,500 survey participants where we collected all this information about humans, about like their demographics, about their location, about the things they were interested in. And then they were allowed to interact with these models, and we collected information about their preferences. And what we found is that there's a lot of variation for different reasons in terms of what humans like. So that can be kind of idiosyncratic depending on the particular individual's preferences. It can be based on what the conversation is about. It can be based on group characteristics that a particular individual kind of conforms to. And this is not really the picture you get if you look at, say, a standard leaderboard. Say if you look at, LLM Arena. You see a model at the top, you see a model at second, and you think, oh yeah, this is the best model for everything. But when you break it down to the individual level, it gets a lot more complex and a lot more nuanced than that. And that's why I think personalization is particularly interesting, because it means we can serve more individuals better if we can find a way to do that well and efficiently, rather than, in a sense, designing for the average user's preferences. And the average user's preferences is also a bit of a stretch, because in practice, a lot of this preference data comes from annotators who are paid, who are kind of centralized in particular locations, who don't really cover the kind of full spectrum of diversity that this study does. So I really recommend reading through this paper. There's, I think, over 100 pages. It's quite detailed, but there's a lot of interesting insight in there. And so one thing I think that personalization allows us to do is keep our sight on the real goal. Now, this is very underdefined. We don't really know what it is. Human feedback gets us quite close. Verifiable reward, all these other forms of signal get us closer and closer. But ultimately, maybe there isn't one goal for everyone. And what people want differs based on who they are. Another thing we can do in context is self-correction. And this is recent work by Lisa Alezraki. And what she looked into was, what kind of information can we provide the model with in context to get it to perform better? And there's a lot of interesting works on kind of critiques and the way you structure critiques to get the most out of model performance. And quite surprisingly, what we found in this paper is that actually just telling the model it was wrong was really, really effective. In many cases, you didn't need critiques, even if they were like highly curated. You could just tell the model its response was wrong, and it would implicitly figure out, based on that information, what the right response should be. And in particular, on these kind of mathematical reasoning-oriented tasks, we saw that it outperformed this explicit signal quite substantially. And there's various hypotheses for why this might be. Things like, well, maybe you're overloading the model with too much information, and that's potentially confusing when you're giving it these critiques. Maybe you're over-constraining the model, and so if the critique is wrong or noisy, the model thinks it needs to abide by what's said in the critique, but it might not, right? It might just be entirely wrong. But this we think was, well, surprising, to say the least. There's also this question of, more context. I've mentioned quite a few times that at some point you run out of context, and there's this recent work last year asking, effectively introducing a benchmark, evaluating what would happen if you bypass retrieval entirely. And now that we have these long context language models, can we get all the documents that exist, throw them into the context, and get the model to effectively do the retrieval over the tokens through kind of the attention substructures. And what this work finds is that performance with the retriever, or throwing everything in, is actually very similar, which is incredibly interesting. And while it might not be as efficient, there are ways to make this process more efficient, especially if your documents are, like if your document set is fixed or doesn't update very often. For example, if you using KV caching and other compression and efficiency methods. Again, let's quickly talk about challenges. So more context means you have more tokens, which is not unexpected, but in some cases it might not be a good thing. And this is from work that Sander led, which was presented at the MLP. And say you have this query, what does add language specifier text mean? And the model replies something like, the string checker flag is actually a flag emoji. The model's given us a response which seems entirely unrelated to the user query. And that's not the kind of behavior that we want from these systems. And the reason this is, or one of the reasons this is that tokenizers are fit on large corpora, often a subset of the final data set that you train the model on. And they're also very complex, and they've got all these tokens in there, think like, something like 15 forward slashes there with a space and then another 15 forward slashes. And there's all these tokens in there. And I really recommend looking through some of these tokenizer configs. And it's usually worth scrolling down to the bottom, because that's where the lower frequency tokens tend to be. Although if you do that too much, you might start seeing tokens everywhere, like on my walk-in this morning, where I saw a ship called End of Sequence, which seemed like a strange name for a very nice boat. But what tends to happen is that at some point, you fit the tokenizer using some form of software tokenization, like byte pair encoding, and it's fit to a text corpus, which is typically in the kind of billions of tokens scale. And then, a few moments later, maybe many months later, eventually at some point you'll get down to training your LLM, where we come back all the way to pre-training, and we train the model to predict the next token. And typically at this point, there's quite a large distinction between the corpus that the tokenizer was originally fit to and the training set that you're now going to use to pre-train this language model on all these tens of trillions of tokens. And typically by this stage, hopefully you have a new, more refined, deduplicated, quality filtered version of this data set that the model is being trained on. And this creates a mismatch between the tokens that the tokenizer is fit to and the tokens available to it at training time. And what happens is you end up having these tokens which exist in the tokenizer, which are either heavily undertrained, the model maybe sees them a few times during all of pre-training, or just never sees them at all. And then when you get one of these tokens, as part of the input, the model has never seen this token, doesn't really know what to do with it, and in many cases, gives you strange and unexpected responses. So yeah, in this work, we also present a few ways to detect and reduce the occurrence of these tokens. But the general kind of point I want to make is that longer context is fantastic, but it's not always the solution to everything. In another work, which Lisa also led, we looked at basically generating preambles. And preambles, again, are part of the context. They're the sequence of tokens that come before the user query. And the idea was, can we generate preambles to maximize the performance of a downstream model, which we didn't touch, right? We have an LLM, we want to optimize its performance. We're effectively, to some extent, automating prompt engineering. And so we go through this whole process, and we see, great, good performance improvements with this, what we call reinforcement learning for reverse engineering approach. And so this is a preamble automatically generated for one of the models in this work. And it seems relatively intuitive, right? It's like, this is the best possible way to answer the question and obtain a high mark, read the question carefully and completely, et cetera, et cetera. It's basically giving very sensible instructions to the model about how to approach a task. This is an automatically generated preamble for a different model. And this preamble makes the model better. And this makes me start to wonder, maybe tokens aren't just doing what we think they're doing, right? In some way they might be, but in some other ways, if this all this repetition, it's not intuitive to me. I don't really understand what's going on here, but it's somehow useful to the model, and it makes it better at the task that we're optimizing it for. And again, here preambles are the sequence of tokens before the query. What if this also applied to the sequence of tokens after the query, right? These reasoning traces, these thinking steps, where we often constrain the model to operating on this natural language manifold. What if maybe we just let the model free and got it to generate whatever tokens it thought were best to get the best downstream performance? And finally, I'll wrap up with a quick note on robustness, because that's most of what my prior work has been on. So things like generating adversarial examples to improve model robustness. And I'll conclude with a quick mention of kind of tool use and function calling, and this general idea that LLMs are effectively stochastic systems, right? There's randomness built into the coding. We don't understand a lot of about how they behave. And in some situations, we want deterministic, we want repeatable, we want robust behavior. And maybe what we need to do is kind of narrow that down to a set of behaviors we can control, like how to call a tool, what query to pass to the tool, how to aggregate information from that tool, and have the model use the tools really effectively and in a general way, rather than expecting them to do complex math in kind of parametric space. Okay, thank you very much. I know lunch is next and we're slightly over time, but yeah.